In this lesson, we're going to examine the key characteristics of functions. So one of the standards that we are trying to complete in pre-calculus is looking at interpreting functions, and specifically we want to be able to make sure that we understand the key features of the functions. These are like things like intercepts, intervals where the function's increasing, decreasing, positive, negative, relative maximums and minimums, and some other ones, but we're not going to get through all of these. We're going to be focusing on intercepts, looking at increasing, decreasing, and relative maximums and minimums. So first of all, you need to make sure that you understand that intercepts are points where the graph intersects the x or the y axes. An x-intercept occurs when y is exactly 0, and a y-intercept occurs when x is exactly 0. So a function can have multiple x-intercepts. But in order for it to be a function, there's a limit of one y-intercept. Okay, so let's look at this graph around here where we have a parabola. So parabola has two x-intercepts and one y-intercept, and that's because it crosses the x-axis twice, but only once on the y-axis. And if we had, of course, a graph that crossed the y-axis twice, it wouldn't be a function because it wouldn't pass the vertical line test. So one of the things that always confuses people is in math class, we kind of throw around these three things: zeros, roots, x-intercepts. And they all kind of really and truly mean the same thing. So the zeros are the points at which the function intersects the x-axis. So in language arts, you learn that as synonyms. So these are almost like synonyms. It's just a lot of times when we're talking about zeros and roots, we usually talk about it in terms of algebra. But when we graph that same function, instead of solving for x, we're looking at the x-intercepts are going to give us the same result as if we had solved that equation for x. So to find the zeros, we would set f of x equal to 0 or y equal to 0 by substitution, and then we would solve for x. To find the y-intercept, we would make x equal to 0 and solve for y. Okay, so let's look at these two functions, and we're going to find both the x-intercepts and the y-intercepts. So in the function f of x is equal to the opposite of x minus 5, absolute value of x minus 5 plus 3, we're going to do first the y-intercept because it's usually the easiest. So we're going to go ahead and we're going to replace that x with a 0. So we're going to do f of 0 equals the opposite of 0 take away 5 in absolute value plus 3. This comes out to be negative 5, but the absolute value of negative 5 is 5. Oops, excuse me. And that means when we negate that, we get negative 5 plus 3, which is negative 2, and that is our y-intercept. So the y-intercept equals negative 2. Now we're going to go ahead and we're going to look at how to figure out the x-intercept. So remember, the x-intercept is when you take the function, or whatever y is, function notation, this part right here, and we're going to replace it with a 0. And then we're going to solve this equation to get x by itself. Now remember, absolute value equations, we could have two solutions. So first we have to isolate the absolute value part. So next we're going to subtract 3. And then we're going to divide both sides by negative 1. And so now we have that the absolute value of this expression is equal to 3, which means it could be 3 or it could be equal to negative 3. And based on those two, adding 3 to both sides, we get 6 on this equation and 0 on this other. So this is actually going to have two x-intercepts, one at 6 and one at 0. Now let's go ahead and look at this function. So this one, it's a cubic function, and later on we'll learn how there's a relationship between the maximum number of x-intercepts and the degree of the function. So let's go ahead and factor. So remember, first we always look for a common factor. And I see that, oh, and by the way, I'm going to find the x-intercepts first. So I'm going to set this equal to 0. Then I'm going to see what I have left over when I factor out 1x. And now I see that this is a quadratic, so I'm going to go ahead and factor the quadratic. X minus 7, x plus 1. And later on, when we review what's called the zero product property, but we're not going to worry about that too much right now, I would realize I take each one of those factors, just like we did back in Algebra 2, set it equal to 0, and solve for x. So here's 1, here's 2, and here's 3. And so that means that this graph, if we go and we graphed it, it would cross the x-axis 3 times. 1, 2, 3, in no certain order. Now let's go ahead and do the y-intercept. So for the y-intercept, we evaluate f of 0. So I got 0 cubed minus 6 times 0 squared minus 7 times 0. Well, 0 cubed is 0. 6 times 0 squared is 0, and 7 times 0 is 0, which evaluates to 0. So that means it's going to cross the y and x-axis simultaneously. Okay, next we're going to go over critical points. So critical points are anywhere where the graph is going to change either its direction or shape. So when we're looking over here at this graph, this is a critical point, this is a critical point, and this is a critical point. So this interval here, it's changing a direction. It's going from up to down. So that's why it's a critical point right there, because that's where it changes. On this interval over here, it's changing its shape. It's kind of getting wider. It's going down, but then it kind of gets wider, and then it goes down again. So that's why that's a critical point. And then, of course, over here, it's going from decreasing to increasing, or going down to going up. And that's why it's a critical point. So extrema are points where the graph changes direction. Specifically, we talk about graphs having maximums and minimums there. Sometimes we call them relative or absolute. So this point and this point here are where we change directions. But because this one is how high it got in that area, and this one down here is how low it got in that area, we call them maximums and minimums. Minimums are how low we go. Think of it like a valley. And then this is like the mountaintop. So when we're talking about this minimum here, it really is a relative minimum. And that's because the graph is going to decrease. So this is only the minimum for this area of the graph. Like this one is a relative maximum for the graph because there is no maximum because it's going to be going on and on forever and increasing, going to positive infinity. Okay, now we have a point of inflection, which is where the graph changes shape. So this other critical point right here is our point of inflection because we're continuing to decrease, but the shape of the graph changed. It didn't continuously go down at the same rate. A point with the greatest value compared to points around it is going to be a relative maxima. The point with the greatest value over the entire domain is going to be called an absolute maxima. So looking at this graph over here, this one is relative, but this one is absolute. Reason? The highest, the greatest value for my domain is right here, but in comparison to the points to the left and to the right, this is the highest value. So it's high relative to what's around it, But this one is really and truly as high as that graph goes. Now, a point with the least value compared to the points around it is called a relative minimum, or minima, the plural form. And the point with the least value over the entire domain and function is the absolute minimum. And I'm going to abbreviate. So again, over here, the lowest anything, any y value that we have, is actually right here. So that's why it's an absolute. But this one is the lowest or least y value, only in relationship to this area of the graph, which is why it's relative. So we're going to be looking for relative maxima and absolute maxima for this, and also relative mins, as well as absolute minimums. So looking at this function, I see that it's going to increase and decrease. So first, we know that it goes from increasing to decreasing. It's going to be a maximum, but is it a relative or is it absolute? Well, let's look at the next maximum. So over here, again, it's going from increasing to decreasing. And which of the two is lower? This one, which means that's where we have a relative maximum. And this one, I don't see any arrows saying we're going to positive infinity for y, which means it has to be the absolute maximum. So now let's go ahead and look at the coordinates. So looking at our absolute, it's about 1.5 to the left of negative. So now let's look at our relative maximum. It's about 1.25 to the right. And down from the x-axis, 1, 2, and maybe about 2.75. And I'm just estimating this, and we could also use our graphing calculator to kind of look at what we would get, and we'll learn how to do that next week when I get back to class. Okay, now, do we have any relative minimum or absolute minimum? So minimums, remember, go from when it's decreasing to increasing. So as I'm looking and tracing this graph, I see that it's going from decreasing to increasing right here. But these arrows say that my range is going to go on to negative infinity, which means there is no absolute minimum. This is just going to be a relative minimum. And so it's just a matter of determining approximately what those coordinates are. So it's just slightly to the right of the x-axis. So let's call that about 1/4. And it's 1, 2, 3, a little over 4 below, which would be negative 4.25. So there we have estimated, by using our graph, the relative and absolute maxima and minima. Okay, now we alluded to this already, increasing and decreasing behavior. So we read a line of text from left to right. We read a graph from left to right. So if I'm starting on the left and I'm tracing this, I'm going up. When I'm going this way, I'm staying flat. And when I'm right here, I'm going down. So I'm decreasing. Okay, so now let's write that in interval notation. So we're increasing over here. So this is from negative infinity until I get right here where x is -1. So we would write negative infinity to -1. -1 gets a parentheses and as well as negative infinity. Now the reason we don't put in interval notation, we don't put a bracket, is because when we get to -1, it's neither increasing nor decreasing. So now when we get to this segment where we're flat, that would be a constant on the interval. And so it's starting at -1, and it's going until I get to over here where x is 4. And again, just like in that previous one, at -1 and at 4, it's neither increasing nor decreasing nor constant at that moment. And then finally, let's look at that last interval. So we know it's decreasing, and so x is at 4 when we start decreasing, and then it goes towards negative infinity. And of course, infinity always is going to get a parentheses. But again, at +4, It's not technically decreasing. So as soon as we get past the 4, then it actually is decreasing. Okay, so let's go ahead and identify where this function is increasing and decreasing, etc. Okay, so let's look at where it's increasing and where it's decreasing. So if I go ahead and I see from negative infinity until I get to right here, it's decreasing. And I see it decreasing on this interval as well. Whereas this interval right here is where it's increasing, and here it's increasing as well. So now let's go ahead and write those in interval notation. So it's decreasing from negative infinity up until we get to here, which is about where x is 0, as well as it's going from right here where x is about 1 to over here where x is going towards infinity. And it never has a constant because it's not flat. Okay, hope that helped. Lots of vocab, huh?